Today we are demonstrating Xilinx's new SDSoC development environment for all programmable SoCs and MPSoCs. SDSoC provides a unified ASSP-like C, C++ programming experience with an easy-to-use Eclipse IDE and a comprehensive tools platform for heterogeneous Zynq family SoC and MPSoC development. SDSoC includes the industry's first full system optimizing C, C++ compiler that provides automated software acceleration in programmable logic combined with system connectivity generation. In this video, we will see how to create a simple image processing pipeline to detect motion and to insert motion edges into a live HD 1080p video stream running at 60 frames per second. We begin by creating an SDSoC project for a base platform called ZC702 HDMI. This platform is built on the ZC702 Zynq development board, supports Linux applications, and provides basic hardware and software support for HDMI video input and output. Let's take a quick look at the application code, jumping directly to the main processing loop. As shown in the block diagram, the pipeline operates concurrently on two video frames, current and previous, filtering, comparing, and combining them to identify moving objects within the video stream. Notice how the function calls mirror the structure shown in the block diagram. Now our first task is to determine which parts of the program should be compiled into programmable logic. As a rule of thumb, if you can run your code entirely in software, you should. But when you need more performance, you can offload compute-intensive portions of your program into hardware. We ran our program as pure software and achieved only about 1 frame per second, so we definitely require hardware acceleration. Recompiling the program using the standard gprof profiler, we found that over 95% of the runtime was spent in the subfunctions of the image processing loop. So let's use the SDSoC estimation configuration to get a sense for how much speedup we can achieve by moving these functions into programmable hardware. In SDSoC, we specify functions to run in hardware by selecting them in the IDE and marking them for hardware. With this simple gesture, we instruct the tool to make all of the necessary changes in underlying compiler and system generation processes. Moving a single function from software to hardware usually requires many steps within software and hardware design tools. With SDSoC, you still retain control over every key design decision, but the tools handle many of the time-consuming and error-prone operations, thus dramatically increasing your productivity. We'll mark all of the functions within the image processing pipeline for hardware. For performance estimation, SDSoC first compiles each function selected for hardware to obtain a performance estimate for the function itself. The system compiler then analyzes the program to determine how the CPU, hardware functions, and memory are logically connected. It then determines how best to implement the program's data transport using a library of data movers such as simple mode, scatter-gather, and 2D DMA. By combining system topology, hardware function estimates, internal characterization of data movers, along with the required data transfers between hardware functions, SDSoC then computes an overall estimate of the program runtime. In this way, we can explore the hardware-software interface before having to commit to a full FPGA compile. SDSoC automatically instruments the application code to baseline the time spent in functions marked for hardware. We click on the link in the report viewer, and SDSoC computes its performance estimate. We can see that by moving the image processing pipeline into hardware, we get an estimated speedup of about 60x, which is in the range required by our application. From the resource estimates for the accelerators, it looks like the design should fit comfortably into our targeted Zynq part, so at this point, we are ready to generate hardware. Having marked the functions for hardware, we can now build the system. Before doing so, however, we will instruct SDSoC to insert a hardware performance monitor IP block into the system so that we can monitor traffic between programmable logic and the Zynq processing system when we're running our application on the board. Under the hood, SDSoC compiles hardware functions into IP blocks, generates the hardware system, and invokes the Vivado design suite to generate the FPGA bit stream for our application-specific image processing system on chip. Our application software must now control hardware accelerators and implement data transfers to them. SDSoC automates this complex set of steps by integrating the application with any necessary drivers, for example, for DMA. It does this by generating system-specific software code and calls into data transport APIs to implement all data transfers and to control the accelerators. It then compiles and links this generated code with the application. The end result is a complete hardware, firmware, and application executable in an SD card boot image. This entire process takes some time to complete, so we'll jump ahead and look at the finished results. We copied the generated boot image onto the SD card, inserted it into the ZC702, and powered on the board. After Linux boots, we run the application, this time with programmable logic accelerators, and see that the video now runs at full rate. The SDSoC environment inherits many capabilities from Xilinx's SDK tools, including a performance analysis perspective. As our application continues to run, let's take a quick look at the traffic between memory and the image processing pipeline running in the Zynq programmable logic fabric. In this demo, we have, of course, barely scratched the surface of what you can do using SDSoC to target Zynq SoCs. But we hope we've sparked your imagination for how SDSoC enables you to work in a software design environment to build application-specific systems on chip in Zynq all-programmable devices. Thank you for watching.